warahmatullahi wabarakatuh, and very good morning. So we are now in week 7 and we're going to discuss, basically it's the third week that we are going to discuss on DC machines. So if we were to revise a bit, or if I could recall about what we have learned previously in the first 2 weeks on DC machine. The first week we have learned basically the basic operating principle of DC machines. We have looked at the construction of DC machines. We have talked about, for example, the interaction between currents and the torque, the interaction or the equation that relates between the back EMF and the rotational speed of a DC machine. That was week 1. And then in week 2, we have talked about basically the characteristic of the machine as it operates in different modes. So it could operate in steady state where the speed and the torque is constant. And then we also have last week discussed about the characteristic of the machine. So all the equations that interact between in the machines as the machine is operating in transient cycle, where you have a certain, for example, a certain acceleration in the machine due to, for example, due to load or even just starting the machine. So in this third week of discussion on DC machines, what are we going to look at is basically we're going to look at basically what we call as excitation types and quadrant of operation. So excitation types means in first week we have learned that in DC machine we would have a field, electromagnetic field created by the field winding or permanent magnet on the stator part. So in stator part there will be a field, magnetic field, create a magnetic field in which we will have an armature in the middle that will also be delivered by a certain current to produce its own magnetic field, and the interaction between these two armature and a stator field that will create the rotational force or the torque of the machine. So today we're going to look at is how do we create that excitation, how do we feed the machine, or in a simpler word, how do you feed the machine with electricity from the power supply of both those armature and field winding. Okay, and then later we'll talk about quadrant of operation, meanings basically quantifying or identifying the type of power that we are either delivering or receiving from the DC machine. So let's begin. So as we have discussed in week 1, we know that DC machine its main principal components are divided into two: the stator and the rotor. So the stator basically produce what we call as a magnetic field inside a certain area, where you have later in it an armature which will be fed with a current as well to produce its own magnetic field. So the interaction between the magnetic field of the armature or the rotor with the field by the stator will create basically the torque, right? So for the purpose of illustration in understanding the type of excitation of the machines, we are going to take as an example a machine of 4 poles. So this is the figure of a machine, a DC machine with 4 poles. What does it mean to have 4 poles? Having 4 poles mean we have 4 magnetic poles or 2 pair of magnetic poles. 2 pair magnetic poles mean we have 2 north and south. So here there is 1 north and south. Here there is another 1 north and south. So 2 pair of poles or 4 poles. And these poles are basically can be created either by electromagnet or by permanent magnet. So if the stator field are created by permanent magnet, then there will be no further discussion, where you would have the field created by permanent magnet, and you wouldn't have to basically think about the excitation or thinking about how are we going to fit in terms of current into the stator field. But what we're going to discuss now is other than the excitation using permanent magnet. So in DC machines, you could, in the stator field, you could either use a permanent magnet to create the field, or we could use an electromagnet. So electromagnet, what is it? It is basically an inductance or inductor, a coil like this, where you feed it with current. So you have learned in basic electrical principle probably in your subject in first year or second year, that when you have an inductor, a coil that you feed it with current, so you're going to create a certain magnetic field around the coil, so it acts exactly just like a permanent magnet. But the advantage of it is that you can control the intensity of the current, therefore controlling the intensity of the magnetic field that you create using the winding or the coils. So here we are going to take an example of a 4-poles machine. We can see that there is a winding on the stator pole. So there is a winding on the stator pole, and then there would be a winding as well on the armature or on the rotor. So on the rotor. So on the rotor, let's have a look at the rotor first. On the rotor, there are 4 brushes noted by letter B over here. So the brushes is basically that it is the component that that's sending the current from the power supply into the what we call as commutator. So we've learned what a commutator is, right, in the first week of the discussion on DC machine. So the current's coming from a power supply, and then it goes into these brushes, and the brushes is basically in frictional contact with the armature, with the commutator. So the commutator would deliver basically the current from the brush into the winding of the armature or the armature winding. So usually what happens is that these brushes are connected in a way to create, of course, those poles, those alternating poles. So here you would have B plus, B minus, B plus, and B minus. So the plus, it will be connected, all of them will be connected to 2 terminals. So it is a DC machine, so it's just 2 terminal plus minus terminals. So these terminals of A and A1, we're going to call it as A and A1 plus positive and negative terminal, is going to be connected to a DC power supply, a certain DC power supply, right? So by regulating the voltage of these A and A1 terminals, what we're going to do is that we are going to increase or decrease the voltage inside the armature, or the voltage basically of the equivalent circuit of DC machine that we have been treating in the previous discussion, in the discussion of previous weeks. Okay, so this is the circuit that we need to fit for the armature, and it goes the same as well for the field winding. So the field winding, what happened is we have 4 exciting field coils, excitation field coils. So 1, 2, 3, 4. We have coils around 4, what we could probably call as pole or call as teeth sometimes. And they are all connected to another 2 terminals. We're going to call it as F and F1. So it's positive and negative terminals. Of this time, it is not the terminal for the armature, but it's the terminal that is going to be supplied with electricity as well, but it is for the field winding. So from there we can see that, and then another precision as well is that the way that we create this winding, we make the turn of the winding is in the in a way so that we create also an alternating pole, north south. So you can see that, for example, in this first pole over here, the winding goes in this direction, whereas when it goes to another pole, the winding goes in the opposite direction, so as to create basically the alternating north south poles. Okay, so they are usually connected in series and they are brought out together at the terminal F and F1. So F and F1 will be needing another power supply. Okay, so if you look at this, it means that we need to fit 2 components, what we call as armature winding 1 and a field winding number 2. So the terminals of A, A1 and F, F1 need to be connected to a certain power supply, and there is basically when we look at this map over here, chart over here, when we use electromagnet for the field winding, we have basically multiple possibility of connection between the terminals F and A, the terminal of the field winding and the armature winding. So we're going to discuss about that. So imagine if you have multiple machine of 4 poles, and then you could basically on that different machine you could connect the field winding and the armature winding in different configuration. Okay, so the different configuration that we have is basically either to use what we call as separately excited or self-excited. So what do we mean by separately excited machine? Separately excited machine means that we connect the field winding and the armature winding using two different power supply. So here what we have here, for example, in this chart, in separately excited, this part is basically, it looks like your rotor, right? So this is where you measure your back EMF. So this is the circuit for your armature. So your armature is connected to one power supply. So the terminal that we call as A and A1 will be connected to one voltage supply. And here it is illustrated by a coil. So basically it's a field winding, because your field is basically just an inductor, and it is now connected to another power supply. So here we have a certain variable resistor. We will explain a bit after this. So the purpose of variable resistor is basically to reduce or increase the field winding current, so that the magnetic field created in the stator will be more or less intense. Okay, so we have one what we call as separately excited using two power supply. Okay, and then another one is what we call as self-excited. What do we mean by self-excited? Is that both of the armature and the field winding will be connected to only one power supply. So both of them will be connected into one circuit, connected into one power supply. And in order to do so, we have basically three possibility of connecting them. So we know we have two circuit, right? Armature and field winding, armature winding and field winding. We can either connect it using what we call as series winding. Series winding means the armature and the field winding are connected in series. So as you imagine just now, you have in this coil representing the field winding. So the two terminals of the field winding, one terminals of F, let's say F, will be connected to the plus terminal of the voltage supply, and F1 will be connected to the one amateur terminal, for example, terminal A. And then the terminal A1 of the negative terminal of the armature will be connected to the negative terminal of the power supply. So here we have your field winding and the armature connected in series. You can also, in second option, you can also connect it in what we call as shunt winding or shunt configuration. Shunt, basically, the meaning of shunt is basically it is connected in instead of series. The other configuration, what do you have? You have basically parallel. So shunt basically means parallel winding. Parallel means, if you look at the figure over here, you have your armature. Both of terminal of armature are connected basically in parallel with your field winding, and all these two terminals are connected to one power supply over here. So this is what we call as shunt winding. And then the other possibilities is what we call as mix of both. It's a bit mix of both, long shunt or short shunt. So in long shunt, what we have is basically we have the field winding. Basically the field winding, we have a small, in terms of the field winding, there are on the field winding you have one portion that will be a small portion that will be connected in series, and a larger portion of the field winding will be connected in parallel, in shunt. So that's what we call as long shunt. So the larger portion of the winding in field winding is in parallel, but a small amount of the field winding will be connected in series. So in opposite of that is what we call as short shunt. Short shunt means there's more field winding that is connected in series, and a small amount of field winding that will be connected in parallel or in shunt. So what's going to happen, the inconvenience of this is basically in your field winding, you need to separate them into two parts, where one part will be connected in series and another part will be connected in parallel or in shunt. So that's what we call as compound winding. You will have both of a shunt and series at the same time. Okay, so these are the types of connection of armature winding and field winding that you may have in a self-excited DC machine. So the text over here explain basically more or less the same thing. So we make distinction, of course, with the permanent magnet in terms of excitation. If you are exciting your machine in the field, using in the stator using a field created by a permanent magnet, then we will not have any discussion of the excitation anymore. Before we go into explaining the difference between shunt and series, and therefore also compound winding configurations, field winding configurations, we need to understand that a remark, and I need to make a remark that this configuration basically exists before the availability of variable voltage supplies. So what happened in the past, for example, 40 to 50 years ago, we don't have a power supply that you would have in your lab today, where you can easily switch or tune the value of the voltage output of your power supply. So the voltage that they receive in the industrial application are basically fixed constant DC voltage. So imagine if it was tapped down and into 24 volts or 48 volts or 100 volts for that matter. So that voltage is going to be constant throughout the application. So they need to use the available constant voltage. So what they do is they have to choose either shunt or series configuration in order to make do with this kind of constant voltage supply that is available. But today, what we have in modern application, we have a modern development of power electronics that give us a modern converter where you can tune basically the value of voltage to make it higher or lower, therefore changing the intensity of your field winding. So nowadays, basically this type of shunt or series configuration could easily be accomplished also by a separately excited motor. So separately excited motor was not that interesting, for example, 40 to 50 years ago, because even if you are exciting the field winding separately, there is no mean to basically change the value of voltage into the field winding, except for basically if you play with include in the circuit of field winding a certain variable resistor, and you play with the value of variable resistor in order to change the intensity of the voltage of your field winding. So the case that we're going to look at when we study shunt and series, it is basically for the old kind of application. It still exists today in industries, and that's why we are learning it. So we are going to now compare between series and shunt or parallel field winding configuration. So what we need to understand is that the connection, what we are discussing here is basically the connection between the armature winding and field winding to the power supply, right? So as mentioned just now, series mean your field winding is connected in series with the armature. Shunt winding is when you have your field winding is in parallel with your armature. So what we call as field winding is the winding on the stator part, as we can see here. So for the same power, for two motors with the same power rating, so imagine we have one motors that we are going to, so it's the same motor. Imagine you have the same motor but in two sample. So these two motors, one you can basically cable or connect the armature and field winding using series connection. Another one you can use a shunt connection. So how do they compare between the series and shunt configuration? So imagine if these both two motor have the same power rating. So we know when you have the same power rating, basically in electric motors, in electrical machine, what we are generating to create the magnetic field is what we call as MMF. So we have revised this in first chapters in topic 1. So in order to create that MMF, you remember that creation of MMF is quantified by basically the number of turns of winding. So we can see that in field winding. So here we have field winding in this example of motor, and the intensity of magnetic field created by this field winding is equals to the MMF, which is the product of the number of turns multiplied by the intensity of current that circulates inside that turn of conductor. Okay, so for example, in this machine, you can see that there are the 4 poles, 1, 2, 3, 4. So there are 4 poles, and then Ni is basically the number of turns that is inside a coil multiplied by the current that is circulating inside the single conductor of that makes the coil. So for the same MMF, what we need to look at is basically, in order to see the difference between series and shunt winding, we need to look at how the amount of current that we can allow to circulate in this field winding. So let's take a look at series first. So if we have the field winding and the armature winding in series, what we need to know is that if it is in series, they are in series, then the current that are going through the field winding is going to be the same current that will go through the armature winding. Okay, so what happens is that usually, as we can see in the text here, series field winding conduct larger current. Why they conduct larger current? Because we know that in armature, when we have a certain load, we are going to the armature is going to pull a lot of current. So as we can see in transient analysis in previous week, when we have a certain load where the MMF is much lower than the voltage supplied to the machine, to the armature, what will happen is that the small amount of MMF basically is going to be compensated by the product of armature resistance multiplied by the current. So the larger the load, then the larger will be the current. And we have seen basically in several examples that the current that goes into armature can goes up to, for a large machine, for example, 50 amps to 100 amps. So if a large current has to go through the armature, that means in our field winding, a large amount of current will also go through the field winding that we have over here. So knowing that through the field winding there will be a large amount of current, therefore the size of the conductor needs to be very thick, because if you want to circulate a lot of current, the conductor need to be thick in order to be able to carry that large amount of current. So for the same power, therefore the same MMF, if you have a large conductor, right, and therefore a large current, then the number of turn could be reduced. Okay, could be reduced. So when you look at the field winding of motor, if you see that the conductors are large, probably as large as, of course, as large as the conductor of the armature winding, it is most probably a motor that is destined to be intended to be connected in series. And when we have a large number of conductors, therefore to have the same MMF, you will remark that we need less number of turns. So in opposite to that, in shunt field winding, what can happen is that we can allow a conduction of current that is much lower in the armature because they are in parallel, right? So if you look at the circuit here, we have the field winding over here, the armature winding over here. So the RS that we have here, we are going to discuss later, is basically the starting resistor that we will use to basically regulate the current that goes into the armature. So what happens if you have your power supply, voltage supply over here, right? If you see the current is going to go through the node over here, right? The node over here. And then once it goes through the node over here, it's going to separate into two parts. It can go either into the field winding, or it can also go into another part, into the armature winding. So the current does not have to be the same, right? The current does not have to be the same. We can allow a small amount of current through the field winding. Therefore, we don't need a large size conductor. So we can have a smaller size conductor, which is of course less expensive in terms of manufacturing process. In shunt winding, we can see that we could have a smaller diameter of winding, but of course, in order to have the same power rating, the same MMF need to be created. Therefore, we would have a higher number of turns. So in a machine that is intended to be connected in parallel or in shunt, you'll see that in the field winding, you have a lot of small wires that build up the coil of the field winding. Now let's take a look at the shunt configuration, shunt motor. So in shunt motor, like in a separately excited machine, the speed will be constant with the voltage. So it is proportional to voltage. So we will have the voltage supply over here, and as we can see in this curve over here is the curve of torque versus speed. And at a given input voltage, you will be placed at one of these lines. Okay, so for example, imagine if you have a base voltage that give you a base speed of A. If you have no load, then you will be placed at this situation, and as you increase the load, it will act just like what we have learned before. There will be a slight drop of speed when the torque or the load increase, right? So this is what we call as base speed. So as the speed is directly proportional to the voltage supply or the EMF, and the EMF, of course. So it is said to be the machine is known to be suitable for a constant speed operation. So it is suitable for a constant speed operation. For a smaller motor, and then this is a second point. For a smaller motor lower than 1 kilowatt, for example, the starting of the machine will be, we will need a certain starter resistor, what we call a starter resistor, or RS, starting resistor, to limit the current if the motor is switched directly into the supply, right? So during starting, what happened is basically the voltage supply will be switched on, but the switch S will be left open so that the current have to go through the resistor RS. So the resistor RS will limit the current that goes through the armature, and then as the motor start to catch up with the input voltage, what we can do is basically we can switch it. There will be a certain combination of multiple resistor. There will be multiple switch of multiple resistor. So the starting resistance can be progressively reduced as the speed increase. So this resistor could be, for example, the kind of variable resistor. So when you start the machine, the resistor will be high at the beginning to limit the current, but as the machine starts to catch up with the EMF start to catch up with the voltage supply, what we can do is basically we can reduce the starting voltages so that the speed can increase more and more. And as it start to cruise at a steady state speed, we can basically switch completely on the switch S, so it doesn't need to go through the starting resistor anymore. Okay, so why do we say that it is the starting resistor is usually used for a smaller motor than 1 kilowatt? It is because basically the power rating of the resistor is depending on the power rating of the motor. So in order to have a variable resistance, when you have a variable resistance, usually your variable resistance also have a certain range, right? You can go, for example, from 0 to 1 kilowatt, but it's very difficult to have a very high range a variable resistor, or else you should have multiple resistors, which will make it which will make the circuit very big. Okay, so and then what we another point that worth remarking is that we can so this is what we call as baseline, right, just now. So at the maximum voltage, you will have the maximum base speed. But if you want to go further into a higher speed, what we can do is basically just like what we have done in the discussion in previous week regarding what we call as flux weakening. We can increase the speed beyond the base speed by doing flux weakening. So what is flux weakening? Flux weakening means that we will reduce the current that goes into our field winding. So it is through the resistance of RF. So imagine if you increase the RF, then the current that goes through the field winding will be decreased. So if you are decreasing the field the electromagnetic field by the field winding, then you can go basically in a higher speed, in what we call as a flux weakening speed. So you can, for example, if you reduce your flux that created by field winding by a certain amount, you can jump to this line of CD. At no load, will be placed at speed C, or if at full load, you'll be placed at speed D. So this region is what we call as region of flux weakening. Look at the steady state characteristic of a series winding, right? So in series winding, what happens is that the current that circulates in your field winding and that circulates in your armature is the same current because they are in series. So field flux is therefore proportional to the armature current because it is the same current. And if in that case, what we are going to observe as well is that the torque is going to be proportional to the square of current. So let me explain why is the torque is equal to the proportional is proportional to the square of current. So we know that we have an equation that relates between torque and current, right? So we have the equation that was T equals to a certain coefficient K multiplied by flux multiplied by I. So the torque that is generated by the machine over here is going to be proportional to the flux and I. Knowing that it is the same current that circulates inside the field winding and inside the armature, therefore the flux over here is also a product of a certain coefficient. Let's say I'm going to call it as K1 multiplied by I. So if we look at the equation is basically equals to a certain coefficient K1 multiplied by I squared. Therefore, that's what we call T. The torque is proportional to the square of the current. So that's what we mean by here. The torque is proportional to the square of the current in the armature. So there is something that is very interesting here that we can observe. So if the torque is proportional to the square of current, therefore, regardless the sign of current, be it in the signs in direction of positive or negative, so we know that we can have a power supply over here, and then the current can circulate either in this direction or in the opposite direction. But regardless the direction of the current, what's going to happen is the torque always have the same positive direction, right? So it means that reversing the voltage, if we reverse the voltage of our power supply, it does not reverse the direction of the torque. It does not reverse the direction of the torque. So the direction of the torque will always be in positive direction regardless the direction of voltage and the direction of current. Therefore, the machine cannot be used when negative braking torque is necessary. For example, in the case of regenerative braking. So let me explain this in a simpler form. So you know that if you're supplying your machine with a certain EMF over here, the machine will rotate and it will have a certain torque, right? But what happens if the load over here is basically producing a higher back EMF than the voltage? We have learned before, if the back EMF is higher than the voltage, then the machine is functioning in generator, right? Because back EMF is higher than the voltage supply, therefore the current is going to circulate in the opposite direction. So in that case, we are having basically a generator. We have a generator where the current is circulating back into the power supply and probably charging the power supply. In a usual case of a normal machine connected not with a series connection, what's going to happen when this happen, if you are using the motor, if you are for example the passenger or the driver of an electric vehicle that using that motor, you will experience a certain braking force. So you are descending a slope, for example, when the back EMF is higher than the voltage supply, you will experience a certain braking. So that your vehicle basically the acceleration is gonna slow down. You are going to experience that. It is just like in your normal ICE vehicle, when you shift down to lower gears, when you goes down a slope, right? You experience a certain braking by the gear. So it's the same case in electrical machine. You will experience a certain braking by the machine. But in this case, in this particular case, if you are connecting your field winding and armature winding in series, you will not have that negative braking torque. So your vehicle will continue to slide down without any reduction in its acceleration. Okay, so there will be no negative braking torque if the direction of the voltages is inverted. It is because the torque is proportional to the square of current due to the same current that circulates in armature winding and field winding. So that is for current. So now what is the relation between torque and the voltage? So if we look at this graph over here, this is the graph of the relation between torque and speed of the machine. For a constant voltage supply, so if you are supplying a constant voltage, just now when we are looking at the shunt machine, we have basically a constant speed, a constant base speed as the voltage is set. But now, what happened in series machine, for a constant voltage supply V, the current varies inversely with the speed, right? The current varies inversely with the speed. So what happened is that we are going to have the inverse square of the current of the speed over here. So as the speed increase, the torque is going to be drastically decreased with the inverse square equation. Okay, so at a specific voltage, this is the curve of the machine. If you have a higher load, so basically imagine if you have a base voltage, you're gonna be placed at this point. But if the load increase, what's gonna happen is the speed is going to be reduced the speed is going to be reduced following this line. Okay, so following this line. So it's the same thing as, imagine if your machine at the beginning have a certain load, so the machine rotate at this speed. But if you leave out the load, you take out the load, the speed of the machine gonna drastically increase following this line as the load decrease. Okay, so what we can say is that at starting resistance is required to limit the current, except for very small motors, because we know at a starting speed, when the speed is low, the torque is very high. When the torque is very high, therefore the current is very high. So at starting, we need a starting resistance somewhere in the machine, in the circuit, to limit the current. The starting torque is very high, so we may have it allows an application that have a very high starting torque. Of course, there will be limit. Is not continuously going to increase into infinity. There is a maximum torque that is related to the value of maximum current that you may have. So the starting torque is very high, so therefore this machine is usually very suitable to be used for high acceleration and for utilization in high load utilization, where the torque resistance torque is very high. And then regarding the no load speed, if you have no load, the no load speed is very high. You can rotate at a very high speed, but of course it will be somehow limited due to mechanical safety, because you know when you rotate a shaft, what happens, you have a centrifugal force, and your machine might disintegrate if the structure is not strong enough to withstand that speed. So large motor, very large motor, should never be run without load, because very large motor have a very large inertia. So if it rotates at very high speed, then the centrifugal force is very high, and it might damage the motor. So large motor is usually, of course, it is used to have a high torque. So therefore the load is always attached, and we do not allow a large motor that is connected in series to be operated with no load at all, because the speed is going to be very high, and it's very dangerous for the mechanical integrity of the machine. So that is the main difference between series and parallel or shunt machine. Series, usually traditionally we calling it as a machine for high resistance torque, for high load, and shunt machine is usually known for a machine that is suitable for maintaining a speed at a certain base line speed, so to control the machine at a constant speed. So it's known as a constant speed machine. Series machine is known as acceleration machine. So that's in general the most important distinction between shunt and series. And of course, we are not going to discuss further on compound motors. Compound motors basically is the combination of both, having the advantage of shunt and series, and having the inconvenience of both as well. So if you have in compound motors, basically if you have more series rather than shunt, then you would have more advantage of series, and if you have more winding in the form of shunt rather than series, then the machine is more suitable for usage, such as in shunt machine. Okay, So that's all about the configuration or the connection of machine for its field winding excitation. So what we're going to look next is basically we're going to discuss about the quadrant of operation when we talk about the machine being generator or motor. So here are the four quadrant of operation of motor. So the four quadrant is basically it is the distinction on the type of power that is delivered or received by the machine. So we divide it in four quadrant where you have the axis Y is the torque and the axis X is the speed. We are calling the quadrant 1 that's starting over here and going like geometrical direction. Clockwise direction, not like in geometrical direction. 1, 2, 3, 4. So if we look at the quadrant, so for example, if you look at quadrant one is the quadrant when you have a positive speed and positive torque. So what does it mean to have positive speed? Positive speed means it rotates in, for example, a clockwise direction. If it rotates in negative speed, it means it rotates in the opposite or in counterclockwise direction. What does it mean to have positive torque? Positive torque, it means that the machine is supplying torque, right? It is supplying torque. The machine having negative torque, it means that the machine is braking. It has a braking torque. So instead of having the torque to accelerate the machine, it is having a torque to decelerate the machine, to reduce the acceleration of the machine. Okay, so for example, if we are in this quadrant where we have positive speed and positive torque, it is basically the normal operating quadrant of a motor. So you are rotating the motor in clockwise direction and it is producing torque basically to accelerate the machine. So the opposite of that is basically the quadrant 3 when you have the negative speed and negative torque. Negative speed and negative torque means that the speed is in the opposite direction and the torque is also in the opposite direction. Therefore, you can imagine that instead of just now the machine is rotating in counterclockwise and accelerating in counterclockwise, now the machine is rotating in counterclockwise and it is accelerating in counterclockwise. So in this quadrant 1 and 3, it is the quadrant of motor where the speed and the torque are in the same direction. So it is not braking the machine, it is accelerating the machine. The speed is either in one direction to the right or one direction to the left, but in both cases the torque are also in the same direction, accelerating the machine towards, right? So in opposite to the operating mode of motor, we have the operating mode of generator that you can find in quadrant 2 and quadrant 4. So in quadrant 2 and quadrant 4, what is the difference between quadrant 2 and quadrant 4? It is basically just the direction of the rotation. So in quadrant 2, the machine is rotating in, for example, to the right with clockwise direction. In quadrant 4, the machine is rotating in counterclockwise, so in opposite direction of quadrant 2. And in terms of the torque is basically in opposition to the direction of the rotation. So for example, if we are in quadrant 2, if the machine is rotating clockwise, but what happened is the torque is in the direction of in negative direction over here. So it is in counterclockwise. So the motor is moving forward, but the torque of the motor is basically decelerating the machine. So when it is decelerating the machine, it means that basically the current is not going into the same direction as in quadrant 1. The current is going in the opposite direction. Why? It goes in the opposite direction because basically what is happening in this generator is that the back EMF is higher than the voltage supplied to the machine, right? So if you look at the difference between this motor and this generator, so they are both rotating in the same direction. So how do we observe that the motor is rotating in the same direction? It's by looking at the back EMF. So the back EMF in the same direction, right? But if we look at the current in this motor is basically in opposite to the back EMF. But now in generator, the current is in the same direction as the back EMF. Why? It is because the back EMF is higher than the voltage supplied. Therefore, the current is going to recirculate back into the voltage supply. So the same happens for in quadrant 4, but instead of having direction of rotation in positive direction, now it has a speed in negative direction. So the explanation over here is basically the explanation of what I have been explaining just now, is the 4 quadrant. So quadrant 1 and quadrant 3 is what we call as the motor quadrant. Quadrant 2 and quadrant 4 is the generator quadrant. So if you want to verify whether your machine is operating as motor or generator, you just have to look at the direction of current and compare it with the direction of back EMF, because in motor the current should goes into the armature, so back EMF is in opposite direction to the armature. But in generator, the current goes from the armature to the power supply, so the current is in the same direction of the armature. So that's all about our discussion on quadrant of operation. And just now we have discussed about the different combination of basically connection of armature winding and field winding, which were the shunt winding and series winding. So what we're going to look next, so the fourth week of discussion on DC machine, we're going to discuss about the control of the machine. How do you control the speed of the machine? So it's a bit of power electronic, and that will be the last week of discussion on DC machine before we go into induction machine. So thank you very much, and I'll see you next week.